Okay, so the video is now recording. All right, so basically reinforcement learning is a technique that has been around for a very long time. It's actually before deep learning. It was his own idea. Then over the years with deep learning, it has been enhanced, and deep learning has just added algorithms to reinforcement learning so that you now have deep reinforcement learning. But the principles of reinforcement learning were still there, and they're still being applied today. Now, the application of reinforcement learning is very interesting because it has new types of applications. And that's really one of the things that I'm going to talk about today is basically how reinforcement learning is different than, say, in machine learning, supervised learning, and unsupervised learning. So we'll talk a little bit about that. So let me just, so what are the applications of reinforcement learning? So reinforcement learning nowadays, along with a lot of other tools, is being used for, games, right? So a lot of, if you remember, the 20 years ago, IBM built this computer, Deep Blue, and it basically beat the world champion of chess, right? And that was a very heuristic algorithm. So it had a lot of rules that were handcrafted by experts, and it had basically a search space, a search tree, and it would go, and look at possibilities of how to play chess. 20 years later, nowadays, you have something called AlphaZero, which is basically an algorithm that uses deep reinforcement learning. This one, the difference between this one also beats chess, but the difference between this one and the old algorithms from Deep Blue and on is that it doesn't require all the handcrafted tools. Okay, so you would do a lot of handcrafted tools back then. So anyway, so I realize I've had this with nothing on the screen for a while. So that's the idea. Okay, so you have, AlphaZero nowadays versus Deep Blue, and really the difference is, so back in 20 years ago, for games, right? So we're talking about games, how to play games, video games or board games or whatever it is, anything that can be simulated. And we're talking about chess. And so 20 years ago, I guess it was like in around 2000, sometime around there, Deep Blue. Was it Big Blue? I think it was Deep. No, it was Big Blue, probably. Something. If you guys remember, I think it was Big Blue. And it was from IBM, the IBM system that they had then. But it was a whole bunch of handcrafted rules, right? So a lot of rules-based.
It is deep. I just looked it up.
Oh, is it deep? Okay, yeah. So maybe they were anticipating deep neural nets. Deep Blue. So it's rules-based, but it didn't really have neural networks. It was just basically if statements, right? If statements. You had to search in a tree. You had to do the search, and the searches are still part of this. You'll use whatever tool is necessary. But what I'm saying is nowadays, with reinforcement learning and also neural nets, deep neural nets, etc., you have systems that play just as well. They defeat the champs of chess, right? So humans really can't play against computers because even though chess is a fun game to watch people play, the computers are better. So that's one thing, that there is no human today that can beat a computer. One of these computers, I should say. So, and then, so reinforcement learning, the difference though is that it's not rules-based. Okay, and that's an important distinction because instead, the algorithm has to learn on its own. Okay, it has to learn, you know, what it's going to do. Okay, and so that's really great, because think about how long it took, you know, how many masters of chess IBM had to hire to work with software developers to develop all these rules and all these searches and everything. Whereas, you know, reinforcement learning, you know, somebody that knows reinforcement learning and maybe has a little bit of knowledge of chess, you know, maybe they can play, but they're not a master, but they could still create an algorithm that can just learn on its own, that can play against itself, that can play against another RL. You know, these are called agents. Whenever you refer to them, they're called agents. And basically, but they're, you know, they're just an algorithm that's doing this. Okay, and so that's where we are today. So this is around 2000. This is 2021. You know, we are there. So it's been pretty amazing, actually, what has happened. And so it started from chess, and today, you know, you can play various board games. Nowadays, that problem has pretty much been resolved. So, you know, so obviously, I'm not going to talk about reinforcement learning like from the 50s to, let's say, 2010, right? So I'm going to kind of skip that. But I'm really just talking about in the last decade or so, where the amazing things have been happening, okay? And it's all thanks to reinforcement learning. So where we are is, you know, recently, like AlphaGo and AlphaZero were developed. If there's actually on Netflix, there's a documentary called AlphaGo. I highly recommend it. You know, if you don't have anything to watch on, you know, find AlphaGo. I believe it's on Netflix. It might be on YouTube. I can't remember honestly, but check it out. It's kind of a won't go into all the technical details, but it'll give you a little bit of history of that. It's a game. It's like chess, I believe, but I've never played Go. But I know it's a famous in other places game. I like to play chess, and so I kind of get that game. And so AlphaZero came later, and basically the idea was, okay, AlphaGo kind of defeated the masters of Go, right? So it played that game. But again, you know, the people that complain about AI say, well, yeah, we're still building algorithms that can do one specific task really well. But when you apply them to other problems, they're terrible. So what AlphaZero tried to do is basically say, well, I'm going to build an algorithm, and this algorithm will play Go, chess, and I believe the other one is called, I should have looked this up, shogi, something like that. And this is the Japanese chess. This is Japanese chess. So if I got it wrong, just look it up. It's Japanese chess. So why is this important? Because there's an equation out there in AI, and I'm not going to go into the equation, but basically it's a principle that says that an AI, the way that you measure an AI, it's by its ability for the algorithm to generalize really well to a lot of problems. Okay, that's really the measure of AI. If you really look at it, if you really look at AI, just from the point of view of how do you even measure AI? Well, you know, think of yourselves, right? You know, you guys are learning machine learning, you're learning cybersecurity, you're learning, you know, web development, Linux, whatever, all kinds of things. But at the same time, you learn how to drive a car, you know how to ride a bike, you know, and you know how to play video games. So you learn all these things, right? You're a good AI or a natural AI, a natural intelligence, because your algorithms generalize well to a lot of problems. You know, you can learn in a lot of problems. And so a lot of the direction in this has been going towards agents, again, the algorithms that generalize really well to various problems. Go, like Go, chess, and shogi. So this algorithm played all three games, did really well in all three, and it didn't really know anything about the game. It just obviously you need to tell it the rules, and then you encode those in the program. We'll talk a little bit about that, and then just it learns, right? It just learns. Then after that came Atari. So I'm sure you guys have heard of Atari or maybe played it. And so, Space Invaders, all of that. And those are more complex games, but they're still 2D games, right? So 2D games where you have a little, ship that's firing, and then there's like the monsters or whatever that it's fighting the aliens, right? So that's Atari. Another problem that has now been solved. In this problem, the game actually can get images, right? And it just takes one shot of where things are, and then there's a lot of problems that need to be solved related to that. But all of them are, as I said, related to reinforcement learning. And today we're just really going to talk about, we're not going to talk obviously about deep reinforcement learning or anything like that. We're just going to talk, and in particular, just one algorithm. As I said, this could be a semester course or it's a pretty big topic. So I just picked one topic that has been of interest here. So a lot of these techniques have been solved actually with one algorithm. Obviously they make changes to the algorithm, but the central idea has been something called Q learning, not to be confused with other Qs out there. All right, but Q learning is an algorithm that is very powerful, right? And so we'll take a look at that today. So this is kind of where the state of the art has been, okay, for a while, but people, are now looking at other problems, right? So they're looking at 3D. They're looking at robots, right? So the robots, like there's that robot Asimo, I think, from Honda. There's also Spot. I don't know if you guys have heard of Spot. Spot is the robot from Boston Dynamics, and it's like a platform for for a cheetah, I think. But they've made simulators about it so that people can actually, in the simulator train Spot to do things. So I think obviously first you're going to train in a simulator, and then you're going to deploy the agent to the physical hardware. You don't want your hardware to get damaged, of course. Especially when it cost, I think Spot costs like $80,000, somewhere along that. So, and it's also been applied to flying, right? So to just like, well, I should say self-driving cars, right? So a problem that they apply it to is like parking in a parking lot or driving, aviation, like autopilots. So this is something that I actually have been playing around with. So I'll show you, just to kind of show you that it's not impossible, right? I don't want you to think that only Boeing can do these things. I know Boeing actually, no, it wasn't Boeing, Airbus, the other one. Airbus recently developed something, I was looking at it, very interesting, of how they wanted to land their planes, not fly them in the air. That's obviously that can happen, but land them, right? Land them via AI, machine learning. And so they use some of these techniques as well. So I have a little clip here, and it's just something that I've been working on. It's not very complex, but it actually does work. So I kind of want to share that. I have one of my grad students is working on this. Hopefully you can see it, right? And then if you notice, I'm using here a software called X-Plane 11, which if you've ever played like Microsoft Flight Simulator, maybe many, many years ago, I know there's a new one now that just came out, but X-Plane 11, I've heard that actual pilots use it for just, kind of awareness and just looking at things, looking at routes, but they say it's pretty, as simulators go, right? It's pretty realistic. Obviously being 4,000 feet on a plane, probably very different than sitting in your home. But from the point of view of just teaching an algorithm, it's pretty solid. And here, what this algorithm is doing, if you notice right now, it's kind of just drifting a little. It drifts a little bit to the left, a little bit to the right. So the basic idea is that we basically have a Python reinforcement learning algorithm, and it's learning how to stabilize the plane, right? So, when it's going too much to the right, it turns to the left, and so on. So we're working on it. I mean, it's a first initial thing, but it at least it exemplifies really well how this works. You see how it was going to one side and it corrected there. Okay, so the idea you can see here on the left side, there's like a little menu, and you can see it says game number 16, and move is 20 something. So basically, it's like it's doing. Oops. Did it end? Okay. So what happened there is that the game it plays all these games, right? So it plays a game, and then it does certain number of moves. So it starts the game again, does another number of moves, and so on. And while it's doing that, there's basically this idea of what is the current state. You can see that's changing. So we'll talk about that, the state of the plane, right? So, that's going to be based on the information that you get from the plane, that the analog indicators that you would have on the dashboard of the plane that tell you position and pitch, roll, and yaw, basically the three metrics. And so you can see the state is changing, right? You can see the state is changing. You can see it's sometimes dipping the wing quite aggressively. That's usually in the beginning. I should say I only recorded this once it was starting to stabilize more. In the very beginning, it's really unstable. And then unfortunately, I don't have it towards the end where it's actually a lot more stable than this, right? So here is somewhere in between, but you can see the states change, right? And there's this idea of penalties that are accumulated, but there's also rewards, right? So, it accumulates a reward or accumulates a penalty. And then the rest is just information about, the different values, the pitch, the roll, and the yaw. That basically just means the three. In a 3D, the axis that it can rotate on, right? So it can rotate to the left or the right, up, down, and then side to side. So that's basically the idea with this. And so we're, as we are getting keeps doing that. As we keep getting information, we are so as we are, as we're making getting this information, and as it's getting the state, it needs to take an action. So the actions, of course, would be to turn the controls to the left, to the right, up, down, etc. You can see there it's dipping a little bit too much to the right, so then you want to turn to the left. And so it's not an easy problem. So here it's very simple what we've done just to kind of demo this, but obviously it requires a little bit more. It can be more complicated than this, is my point. Okay, so it's by no means an easy problem, but I just wanted to kind of show this to motivate, what you can do with reinforcement learning. All right, so this is, so that's just the little video. I wanted to motivate that. So we can go back to, stop it. We can go back to the whiteboard. All right, so that's and obviously you can if you saw that, you can think to yourself, okay, so this can be applied to um, other things, right? So we can apply this to self-driving cars, whatever, robots nowadays. Um, I was seeing now they have these just like Spot. They're building like birds that actually fly with wings instead of having a propeller. All kinds of things. So animal models. You can even apply this to, let's say that you have a nuclear power plant, right, or a nuclear reactor, right, or you have some kind of the steel furnaces that they have, right? And you wanna basically figure out a final state given an initial state, right? So an initial state. So you can basically model this as a game, model this problem as a game of flows of whatever heat around here, and then you can basically use reinforcement learning to kind of do something, take an action, and then try to figure out what's going on, or how to model conditions. So for instance, you could say, well, if this is the initial set, this set of controls, then this is another state I, and then I set another set of controls, and this is state I plus one, and so on, right? So you basically take actions that result in states, and then you end up in a final state where if it's a good state, you win. But you can also lose, right? So that's we all know that games kind of work this way, and that's what reinforcement learning does for you. So that's really all of it, is the motivation. So it doesn't just have to be games. You just, in a sense, what I could say is, I would think there's a lot of problems out there that could be resolved through this, as long as you are able to model the problem as a game, right? As a sequence of steps, which there's that result in a state, and whenever you're in a state, you take an action, and then that results in another state. And at the end of taking all those steps, states, and actions, you arrive at a position where you gain your you reach an objective, or you gain it, you do something, similar to winning the game, basically. Okay, does that make sense, guys? Are there any questions?
I think that makes sense.
So that's basically what it is, and that's really what I wanted to say. Is it's sort of the motivation of it, right? So I find this is actually one of my favorite fields in machine learning. So I find it very interesting. Like I said, today we're not gonna be working on the autopilot or anything like that. It's a difficult problem. Instead, we're gonna be working on we're gonna look at just these games, right? So this idea of reinforcement learning, the basics of it, in particular Q learning, just to kind of see how it works. Okay. So here we have. Now, one thing I want to say is, so how is this, if we want to think of this in the context of machine learning, right? So we have machine learning. Just so we have the context of machine learning here. And really, we said at some point in the semester that machine learning could be supervised learning. Right? And then unsupervised learning. And then we have also reinforcement learning. So really, what was the difference? So if you remember, the difference was that in supervised learning, we had the X and the Y labels, right? So we had a sample 1, sample 2, dot, 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 the features, F1, F2, and then the labels. And unsupervised, so this, you know, we saw this with KNN, we saw naive Bayes, right? We'll continue looking at other algorithms later in the semester after spring break. And then unsupervised is the fact that we only have X, right? So we don't have labels. So we saw this with singular value decomposition so far, right? So we saw that we could do a recommender system. Here we had the samples in our example were the, let's say, the users. They were the users. And then, of course, here was the movies, right? So we had the movies. But we didn't really have labels. Let me just say we didn't need labels. That's the point, because we could have had labels after compressing the data, for instance, as I showed, right? But we don't need the algorithms. Basically, the way that I should say this, I think, is that the algorithms in supervised learning do not require labels, or actually in supervised learning do require labels. In unsupervised learning, they do not require labels. Notice there's nothing here, right? So labels are not required. In reinforcement learning, we have something a little bit different. And by the way, I should say, you know, we'll also cover other algorithms later in the semester, one called k-means, which is a classical clustering algorithm. So we'll cover that towards the end of the semester. It's pretty easy. So it shouldn't take that much. Now, what about reinforcement learning? How is reinforcement learning different? So in reinforcement learning, you kind of have the data, right? So you once again, in reinforcement learning, you do in a sense have labels and you have X. But it's a little bit different because the labels, unlike with supervised learning, where you have the labels beforehand, right? You go in and you go into a forest and you measure all the trees and everything, and you say this is Setosa, Virginica versicolor, or you look beforehand at a lot of pictures of cats and dogs and you say, oh, this is a picture of a cat, this is a picture of a dog. Here in reinforcement learning, you don't do that. You will use the labels, but you don't compute the labels until the algorithm is running. Okay, so basically what happens is that the X is really, so the question is, how does it learn, right? So how do you learn something? So in supervised learning, you look at the samples, right? You look at X, you look at the features, and you correlate to the labels, right? In unsupervised, you look at the structure inside, the individual structure of the data, and you learn. In reinforcement learning, you learn by reinforcement. But the way that you can think of it in this analogy is that here you have, instead of samples, think of it as you have games, right? So you play a game. You take a step. So let's call it step. So you take a step and then another step and then another step. And given that step, you have a combination of the state and the action. So think of a game, right? So in a game, you know, so in a game, what would be the state? So the state would be, give me a sec. So in a game, the state would be what? You know, if it's a board game, right? So you have a board game and you're moving across the board, right? What's the state? You were here and then you went left, so now you're here. That's the state, right? You move from one spot in the board to another spot in the board. So that means that you were here. So you were here, and let's call that state at time t. And then to arrive at this other, at that other square, what do you need? You need to take an action. So you took action. took an action. And the question is, what was the action? Well, the action was you can go up, down, left, right, and then you can go up, left, right? So here you went up, left. So you went up and left. That was the action. Those actions need to be defined beforehand in the game. Okay, so that's something that you need to define beforehand in the game. They're kind of, you know, like any video game, right? Imagine you're building a video game. Well, you would define this is the board, and then these are the actions, and so on, right? So you have to define all of that. Usually that's referred to as the environment. All right, and then once you take that action up and left, what happens then? You end up in this one, and that basically means you end up in state, let's say t plus 1, right? So now you're in the next time spot, and so that's basically how that works. Okay, so you go from one state to another by taking actions. And those are, generally speaking, the things that you will do in any reinforcement learning problem, okay? Regardless of what it is, whether it's a self-driving car, spot the robot, the airplane, games, or modeling, you know, some kind of a nuclear reactor and figuring out something about it. You take this idea of states, take an action, arrive at a different state, and then you use this information to learn, right? So, because you can randomly do things, right? The states exist. Think about it. You can have this this is 4x4, so it has 16 states, but that's a very simple thing. No problem in nature would have such a simple set of states, right? So states will actually be very complex. So that's a big problem that you have to kind of deal with, the explosive size of the states. And then the actions usually don't have to be that many. You know, if you're in a like I said, it's just the controls, right? In the plane, for instance, which might seem very complex, you know, you turn the stick to the left, to the right, pull it forward, pull it back, and then you step on the pedals, right? You know, kick the left or the right. And so ultimately, you end up with about 6 actions. You know, in the car, you turn the steering wheel to the left, to the right, and you hit the brake. And then you might hit the accelerator. And so those are really the things that, you know, it's not that many actions, but the state space is quite complicated. Okay, so give me a sec. Let me grab some coffee. So anyway, so that's the idea, right? That you have those states and actions, and that's why I'm saying here that that's kind of what goes in the X. But how do you learn? Well, usually in supervised learning, you would learn from the labels, right? So then what would be the labels here? The labels would be a system of rewards and penalties. So you have rewards and you have penalty. And so you have this system that, and this is usually called the reward function. So this is actually a function, okay, that you need to define. This is complicated. This is complicated. Okay, so it's not a trivial thing to develop that reward function, because you know you could try to model anything, right? So how do you? That's the thing. How do you know that if you take these actions given these states, that's a positive thing? Especially think of chess, right? So a game like chess, you start, you know, the very first like 7 moves, they're just setting up the game. I mean, you rarely, you know, everyone pretty much plays the same thing. You play that famous, the Queen's Gambit or whatever. And so you start forming up the board game, right? But you're not really doing, that doesn't say who's going to win. So you have to literally play the game, get to the middle game, get to the end of the game. And then once you get to that final part of the chess game, okay, you know, one will win, right? But it's a sequence of states. So if you think about it, it's really, you know, state and then state plus 1, and then, state plus 2, dot, 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 state t plus, oh, that's wrong. State t plus n, right? So you do this entire sequence, and that sequence will determine that you win or lose. But how many of these possible state sequences you have? That's pretty big search space there, right? So only one of these will win, whereas a lot of them will result in you losing. And so this is complex because you kind of have to consider, okay, if I take these actions now in the present, will they lead me to winning in the future? You kind of have to work that in, the futureness of a problem. All right, and so that's difficult, but that's what makes it fun, though, right? Solving something like this makes it, incredibly fascinating, and that's why, believe it or not, the state of the art is kind of where you see the papers that get published in Nature or in those very important journals. I always make this comment that rarely does anything related to machine learning or deep learning get published in non-engineering or non-math journals, right? So it usually gets published in those, but there are journals like the Journal of Science or the Journal of Nature, which are the journals that publish, things like they discovered, a new star, or they discovered some new law of physics, something amazing, right? Breakthroughs in genetics, things like that. And really the only paper in a long time from the area of machine learning that was published in Nature was actually a paper related to one of these games. I think it was AlphaGo and AlphaZero. Both of them were actually published in Nature. And what that tells you is that, and that's important because it's a fundamental thing, right? It's a fundamental move towards real AI. So, so what I'm trying to say is don't go by what I say. Look at the reality of things. Of all the papers, of all the breakthroughs in machine learning, deep learning, etc., the one that got published in such a big venue as Nature, that is AlphaGo, AlphaZero, which are related to reinforcement learning, which tells you there's something pretty special about all of this. Okay, and so I kind of want to stress that. And so the idea, again, with reinforcement learning then is that here the labels would be related to the rewards and penalties. So let's call it the rewards. But just keep in, so this is another element that is complex. How do you, so now you have this game, right? You have this game in reinforcement learning where you have the environment, and in the environment you take steps over time. So you take steps over time, as you saw here. Every step that you take over time can lead into states. So you end up having states, and you also have actions, right? So you start at an initial state, you take an action that leads to another state, you take another action that leads to another state. And every time that you're doing that, you're getting the reinforcement, the feedback based on the rewards, but also penalties. So, a perfect, kind of an example of this is like football, right? So in football, you play the game, obviously, and the reward is advancing, yards or scoring a touchdown, right? And then the penalties are what? Interference, all that stuff, holding. So whatever that is, they push you back, right? So, automatic, whatever, first down if it's the opposing team, or whatever, right? So you end up in the game, which, because that's also a game, you end up being penalized in some way, or you end up being rewarded by getting an automatic first down. And so that it's a similar idea. Okay, it's a similar idea, but all of that is governed by the rules of football. Well, the whole point is that the environment is extremely important, right? The environment is extremely important. So for instance, for that airplane game that I showed you, we used X-Plane 11, which uses UDP networking for communication. So that was really great because all we do is from Python, we didn't write the code, it was written by NASA actually, but we send the commands via UDP to X-Plane. So, X-Plane, take this action, and then X-Plane returns the state. So basically our code, so if we look at it, and I like this approach where you have a sim, right? So in this case, like X-Plane, but it can be anything else, X-Plane 11. And it just via networking UDP, right? We have the game. The game is just running in real time. And then here, of course, we have our Python code. And then our Python code just needs to keep track of state. This also has its own state system, obviously, right? So it has state, where the plane is, etc., all the settings. But here you need to have your own tracking of states. You need to know the actions that you're taking. And then you need to figure out what the rewards are, right? So the rewards, you need to think about that in relation to this, right? So how do you reward so that the plane, so if the plane is going too much to the left, right? If the wing of the plane is, the plane is doing this and it's tipping down too much, well, obviously what you want to do is you want to modify the control so that the right wing starts to go to the right to correct that, right? So it's kind of simple in that sense. So you have to really, so that's a problem that we are actually still working on to get it a little bit better. Obviously, if it's going too much to the left, all we have to do is turn right. So we kind of know that, and that can be encoded into the system. But we want to perfect that a little bit more. And the thing that perfects that in theory is the reward function. However, the reward function is not always easy to model. It's actually the hardest part. Actions are always easy. Figuring out the states, it's encoding, I should say. Figuring out the states is not hard either. But encoding the states, that's kind of difficult. So I'll talk a little bit about that today, and I'll show you the contrast actually between two problems that are somewhat easy and yet it's tough, but the hardest part really is the rewards. Okay, the rewards function is actually quite challenging. All right, so that's the idea. So do you guys understand the difference between supervised learning, unsupervised learning, and reinforcement learning? Does it make sense?
That makes sense to me.
Yeah, so again, it's the difference here, it's kind of you have this in one shot, right, of time. Whereas here it's over time. Our game, you saw the game, right? It was playing 200 moves, 200 actions, basically. Of flight, in flight, that's probably like a few seconds, 5 seconds of flight time, or more, maybe 10 seconds. I'm not sure, but that's really the idea. So the other idea then is, we need to basically figure out an algorithm. So in this case, the algorithm, there are several algorithms, I should say. The one we're going to use is one called Q-learning, just given, this is the one that I'm going to present, given that, well, as I said, it was used by all these techniques, right? So it's being used by all these techniques. And so, it's kind of important. But there are other approaches as well that are pretty important. Now, one recently, there's been some ideas about how to deal with the reward function, right? So how to deal with the reward function. So usually the reward function is something like, well, get the state of the plane, for instance. If it's too much to the left, figure out how to measure this. There's some kind of a indicator in the plane, right, that gives you this, the through physics, through the gyroscope or whatever, they can figure out, okay, it's a bit too much to the left, so make a correction to the right. And that, you know, you can do those reward functions like that. However, what if the problem is completely different? What if the problem is that you have a robot. Let's say you have a robot, right? It's a robot, it's very flexible robot, right? So it's a very flexible robot, right? And the robot, you want it to learn to dance. And you want the robot to learn to dance, you know, like salsa, something. You have the robot, it can move, you know that. And an agent, it's in a simulated environment somehow. So you know the actions that it could take, right? Lift your leg up, down, move your arms, you know the states. Well, if one leg is up, then move it down, or so you know all of that. States are defined, actions are defined, but still, how do you write a reward function to learn how to dance salsa or any type of dance? Do you see the challenge there? And so some people have thought about this, and interestingly, they came up with this idea that it's not bad. So they can write an initial reward function, just some basic reward function, but they can have a reward function that can be adjusted in real time. And what they suggested to do is that the robot starts dancing, right? And it probably looks like it's having a seizure more than, than it's dancing. But at some point, let's say after, 1,000 iterations or epochs, right, of trying to dance, the robot generates a little clip, maybe a clip of like 20 frames or so, and it's going to give you two options. So it shows that to the human, right? So the human person looks at it after 1,000, and basically you see clip 1, and then you see clip 2, right? And in both clips, the robot is dancing. So it's moving, dancing and so on. And all you have, guess what you would have to do? You just look at the two videos and say, out of these two videos, which one do you think looks more like salsa dancing? Well, they look terrible, but if I have to choose, it'll be this one. Do you see that? So this is an interesting approach to this, because you don't have to give it reinforcement every time, right? You don't have to, it does 1,000 iterations, right? And you don't have to give it reinforcement every time. But after 1,000, you give it a little bit of reinforcement. The reward function then will get adjusted based on that. Then it does another 1,000, and again, it shows you a little clip, and you give it. You see, so what you're doing is you're adding the human element to kind of help out rewards, because you might argue that sometimes we know how to do things, but we don't know how we know how to do these things, right? It's kind of this thing where you just say, oh, I learned when I was little, and I have no idea why I'm so good at this, right? You can't really, even us as people, can't really sometimes explain why why is Tiger Woods so good at golf, or Michael Jordan, why was he so great at basketball? What was the reward function? It was hard to figure out, right? And so in that sense, then they've added this element of feedback of a person that just looks at the clip and says, well, this one's a little bit better. And from there, the reward function gets updated, basically. Any questions so far, guys? So that's really just kind of the motivation of this. We haven't gotten to the Q-learning algorithm, but we will in a sec. Any questions?
I don't have any.
So that's really, hopefully this makes sense. That's a new type of algorithm. As I said, it's called reinforcement learning. It's one of the things that I'm most excited about, to be honest. in machine learning. Like I think all the other tools, supervised learning, unsupervised, can make their way in reinforcement learning somehow. But of everything, for me, I work in natural language processing, which is just something I really like. But aside from that, the thing that I find most fascinating, and the thing that I think that will revolutionize a lot, will be this reinforcement learning. Reinforcement learning existed for a long time, but because of all these really large state systems, it couldn't really do much. But then deep learning came in, parallel computing, GPUs, everything that has happened in the last decade, since GPUs, since 2007, basically, when GPUs were made available for gaming, and now for machine learning, basically reinforcement learning now has all the power that it didn't have before to try to tackle very, very important problems. And so, it's certainly a very, very exciting field, I think. And that's why, usually this should be its own course. We don't have a course about this, unfortunately, yet, I guess. But at least I'm covering it enough that you guys have a sense of how it works, and within the context of the other topics that we're covering this semester. All right, so now that we've talked about this, and we've talked a little bit in sense of what everything is, we've talked about this. Now we can talk a little bit about Q-learning itself, or Q-learn. Okay. So Q-learn is the algorithm. I already posted the code on GitHub, so I'm not gonna type it up. You guys can just use it. So I'm gonna go ahead and just go to the website, go to the code. All right, I'm gonna share the code, and I'll show you where I have this. So if you can see here, you should be seeing the GitHub, and then we're going to go to the repository. So, of course, Machine Learning Foundation. So you can see here, I've added the code already. This is taxirl.py. Okay. So before I go into the code, I'm just going to run it. It'll run here on our Windows environment. Now, it doesn't run so well when you have something as interactive as this, as reinforcement learning. It doesn't run so well on the Jupyter Notebook, okay? So instead of running it on the Jupyter itself, we're just going to run it on the Anaconda environment that you guys have, I'm sure, when you installed Anaconda. So all you have to do to get it to work is download this code. Obviously, you'll have to download it to your desktop, wherever you run your programs. And then you can see here, you'll go in your Windows from the Windows icon, right? You will go to the Anaconda prompt, just search Anaconda, and then you'll see Anaconda prompt. When the prompt opens, you can just run pip install gym. And I need to talk about gym in a second. And then once you've installed gym, you can just run the code that I just gave you, Python taxirl. Taxi implies that it's related to a taxi or taxi cab. So let's talk a little bit about it. So what is this gym that I mentioned here? So gym is what in my notepad, or here, the sim. Okay, so in the video that I showed, I was not using AI Gym. Because I have a simulator called X-Plane 11. I actually have, this program. It's like a video game that people can buy. You can buy it from, I forget, Luminar, something. It's a company. And so you can buy it from them, and you play the game. Just buy all the joystick and everything and play the game. And so the sim, and I wrote basically some code here to kind of give the environment. But OpenAI Gym is kind of the same thing. But it's already boxed into a Gym module in Python. So whenever you open up Python, you can open up Gym. And what it does is it gives you prepackaged games with the whole environment. So the environment is just a thing that holds the state, the action, the rewards for that game. So you don't actually have to define those, okay? That's what I want you to understand, is that with Gym, the states are given, the actions are given, the reward functions are written. So you don't have to write them, okay? And then the sim, there's no sim necessarily because Gym is mostly like 2D board type of games, like like checkers or things like that. You'll see what taxi cab is. But basically, Gym kind of pre-packages these things, so you don't have to deal with the states, the actions, and more importantly, the rewards. Okay. Now, if you were doing actual research, like if you have to do your own research, kind of like what I'm doing, me and my student are working on with that plane, we have the sim, right? And the sim defines the states, the actions, etc. But we don't have the rewards because the rewards are, the rewards for a sim are basically you're the human, you need to fly well, right, and not crash. But for an AI agent to learn, we need to define this element of rewards, and that can be pretty challenging for the given problem. However, as I said, with Gym, you have the advantage that Gym is a prepackaged set of games, and it's got the state's actions and more importantly, the rewards. So you literally do not have to touch them. And so that makes working with Gym a lot easier, and you can just focus a lot more on the algorithm itself. Now, if you have to write the rewards, then yeah, that's much more challenging. All right, so that's what Gym is, right? So it's a library in Python that has a lot of games for reinforcement learning. Okay, so then in our code, there's all these elements, right? So there's the element of Q learning. That's an algorithm that's actually pretty straightforward. We'll see that. And then you have the environment, which in like I said, in my plane example, it was X plane 11, and then we define the environment, which basically means the I should say the state encoding, because the states are actually not that difficult to figure out, but the encoding of it can be challenging. Encoding, the actions, those are usually the easiest to identify, and more importantly, the reward functions, which are tough. Okay? So that's usually what you have in these kinds of, whenever you're trying to do Q learning, but conveniently for you to practice understanding just Q learning itself, you basically then have an algorithm, you have in Python, what is called AI Gym AI. So that's a little library, and that's what we're going to be using today. So I already installed it on my program. So let me then just bring it up. So I'm going to bring up the Anaconda prompt. Okay, I'm going to share that. So I'm in the Anaconda prompt here, and then I'm going to go into the desktop. And then I'm going to go into this course. Right, you can see that there. And then you can see here, these are all the scripts, right? You should be seeing this. These are all the scripts that we had in here. Make this a little bit bigger. And you can see I already have the taxi.rl. I already ran the pip install, so you would have to run, you know, pip install gym. I'm not going to run that because otherwise the library will not be available initially. The code, I already tested it, so I already made all the tweaks that were necessary for it to run. And then now you can just basically do Python and then run taxicab. So I'm just going to start with that kind of before we get into the code to kind of illustrate what we have here. So if I run this, you can see it there, right? So I don't know if you guys can see. It's basically a type of board game, right? You see it there, a type of 2D board game, and it's showing you. You can see it's running in real time, right? And you can see it's showing you the time step that it currently is on, right? It's currently showing you the current state, right? You can see the numbers there, state, which indicates the position in and what it's doing. It's showing you what action it's taking, and it's showing you the rewards, you know, what it's computing. So all of this depends on what you want to do in the game. So for instance, here you can see that the actions are pick up, east, west, drop off, south, north, east, west, drop off, pick up. All right, and you can see it. Basically, I think it's 6 actions. What it is basically if you look at this game, right, and I can make it a little bit bigger, I guess. Oh, that's great. So you can see it there. What's it doing? This is supposed to be like a parking lot. Okay, it's a parking lot or something like that, a big parking lot supposedly. So you have the little yellow square is the taxi. Okay, so that's the taxi, and it's a taxi that is trying to pick up somebody and take them somewhere. So they're basically, I think there's these R, Y, B, and G. So these can randomly be set, but what they mean is that, you know, one indicates the location where the passenger is, and one indicates the location where the passenger wants to go to. Okay? So one indicates as I said, the location where it wants to go. So there's a passenger, the taxi has to get to the passenger, pick them up, and then take them to the destination. Now there's these other destinations, and it should not take them to those destinations. It should only take them to the correct destination, okay? So that's the goal. The goal of the game is to pick up the passenger and take them to the right destination. But you don't tell the passenger, you don't tell the game or the agent how to do that. Instead, just by giving rewards based on reinforcement learning, right, the agent is supposed to learn. If you look, there's these lines here, and these lines indicate walls, basically. So, or parked cars or something. So it can't travel through these. It can only travel like where you have dots. But that's not a problem because all of this is already defined in the environment by the game itself, right? So you don't, the rewards are defined, the actions, everything is defined. You just really have to worry about the reinforcement learning part, which is what we're going to talk about. I just noticed there's an error in this code. I just realized that. I think when it finally completes, I forgot. In case you want to do this yourself, I'm pretty sure I saw the error. It said something. It doesn't recognize clear, and it's because it shouldn't say clear. It should say CLC. But I think I changed it in one place, and I think there's probably another place where that clear is located. So when we take a look at the code, I'll hopefully find it. But just be aware of that, because I did see that error just now. All right, so anyway, that's basically the game. So the game has an initial state randomly where the cab is. The cab just starts moving left, right, up, down, until it gets to the spot where the passenger is, or the passenger. And so once it gets to that, it will pick up, right? Picks up the passenger, and then it starts moving until it gets to the final destination, and it drops off the passenger. So it keeps doing this many, hopefully hundreds of thousands of times. Or it doesn't need hundreds of thousands, 1,000 times or so. But hopefully what happens is that once it learns what to do, the next time around, when let's say you let it train for a while, for 30 minutes, once it finishes, and then you run it again just using what it learned, it won't basically take, it should take only a few seconds, right? So the way that you measure the performance of this is that the algorithm, initially it takes a long time because it's kind of randomly trying to figure things out. But once it learns, it'll just go pick up the passenger and find the fastest route given this game to drop off the passenger to their final destination. Clear, guys? Does it make sense? Any questions?
No questions.
No questions. All right. So that's basically taxi cab, the RL game here. So go ahead and try to run this on your home computers. Now the next thing we're going to do is we're just going to look at the code. So I'll bring up, I'll let this run for a little while, and then we'll bring up the code and just kind of start going through it. Okay. So that's where we are. So at this point, I've hopefully motivated enough of what reinforcement learning is. And now we are ready to talk about Q learning itself. Okay, so we'll talk about Q learning itself and how that works. All right, so I'm gonna stop this, and then you can just run this on your own home. Okay, so I've stopped the game. I'm gonna stop sharing that. All right, so now we'll close that. So the next thing we're gonna talk about, since we're getting into the algorithm, is we're gonna talk about Q learning, right? So Q learning. And what is this Q learning? So Q learning is nothing more than a table. Okay, there's a couple of things associated with Q learning, but basically you have a table. So let's think of the board game. Let's think of an easier example. Let's say we have a board game, not like the taxi cab, which is a little bit more complex, but just something like a board game like this, right? So you start here, and then, you want to win the game, right? By getting to the cheese, right? So you're a mouse here. Okay, so what does the mouse do? Well, the mouse, these are like holes that the mouse can fall into. So what the mouse needs to do is, if the mouse goes in this direction, the mouse falls into the hole, right? So that's not a good direction to go in. If the mouse goes in this direction, falls into the hole. If the mouse goes in that direction, falls into the hole. But if the mouse goes like this and like that, the mouse gets to the cheese. Okay, so that's the optimal solution that the game needs to find. Okay, out of all of those, it needs to figure that out. For us, it's pretty easy because humans are intelligent, so you can look at this and really quickly figure it out. But when you're doing an algorithm is doing this, it's not going to be so trivial. Okay, so you got to figure this out. So you got to think in terms of these are as states, right? So you're going to represent states. So this is a 4x4 matrix, which basically means 4 by 4 equals 16. So there are 16 possible positions where you can be in this square, right? So initially, for instance, the mouse was here. So it's in that, whatever that index is, right? And so if you start at 0, so that would be like, you know, 1, 2, 3. So it's at 3. So it's at 3 and 1, right? 3 and 1. So 3 and 1. And so those would be the indices. Basically, you have 16 possibilities, so you have 16 states in this example. And then you have the actions, which are, you know, left, right, up, down, right? So it can go left, up, right, up, right, right? So that's what wins the game, right? So left, up, up, right, up, right. So that sequence of actions is what wins the game in the most optimal way in this very simple thing, but that tells you that the actions are these. So basically what you do is you create a table. The Q learning is associated with something called the Q table. All right, so you create this Q table. I like this because it's pretty intuitive, you know. So you do something where you have the actions, right? You have the actions, and then you have the states. So the states are going to be, there are 16 of them. So that ended up being pretty small. But there are 16 states, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So those are the states, 16 states, which means what square you're on. And then you have over here the actions, which are the possibilities. There's only 4. So you can go left, right, up, or down. You see that? So the idea is, okay, well, for this game, if I'm here, right, if I'm here at this square, that means I'm on state, let's call that one state 4. I'm just, for whatever reason, I'm on state 4, that square. Okay? Then given that I'm there, what's the best action to take?
Left.
Left, exactly. So in theory then, what you would want is you would want a value that says 0.7, and then these are 0.01, 0.02, 0.10. So that whenever you're in that state, you say, okay, what is the highest value here? Oh, 0.7. Boom, I'm going to go left. Do you see that? That's how this works. Is that the Q table initially, though, the problem is initially the Q table has no information. So initially the Q table is basically blank, all zeros. You see that? So it's going to be all zeros. And so you kind of initially, when you start taking actions, you have to take them randomly. So you take a lot of random actions, random moves, but you're hoping that as you take a move and you get the state and the reward, you learn. Okay, you learn, and then as the game progresses, you start computing the correct values that go here. Okay, you start computing the correct values. So that eventually, when you've learned a lot about the game, again, you end up with 0.7, 0.01, 0.02, 10, and so on. And so this table would be filled in. Now the question is, how do you learn those values? So the way that you learn is that every iteration, you're in a state, you take an action, you get a new state, you figure out the reward, you take all of those parameters and you run them through an equation called the Bellman equation. And the Bellman equation is nothing more than a formula that allows you to take previous state, t, new state after taking an action, t plus 1, the action, and the reward, right? You take all that information and you compute a value for the Bellman equation, the Q value, if you will. So for this state and for all these actions, you're going to compute these. So these values get adjusted, right, over time. And eventually, after training, hopefully, this table will be filled in with the correct values so that then you can just play the game. And hopefully, you would have this sequence in there. You see that? So if you're in the left state, 0.7. Then it's going to say now you're in the next state, which is basically you're here. So if you're in that state, then what is the best move? Up. Okay, then you move up here to this one. And then what's the next move? Up. And then you move again and, oh, yeah, there's 2. So here. And then once you're there, right. Okay, and then once you're there, up again. And then once you're there, right, and you win. You see that? But all that information would come from the Q table. And the Q table needs to be filled in automatically as you're learning the game. Okay, as you're learning in the game. Does this concept make sense? Because this is important, guys, because we're going to create this Q table in the code. And so I want you to understand where this is coming from. The code is actually not that complicated. There's basically this idea of the table, and then there's this idea of the Bellman equation. And that's really just one line of code where we compute everything. There's a few parameters, but that's really all it is. So what's important, though, is that given a state, wherever you are, you need to know that state and then look up, you basically get the index of the highest value in this vector, right? So in the index here would be, let's say, there's 4, so index would be 1, right? The first index, and then, oh, well, that corresponds to left, and so you know what action to take. It's actually pretty simple. Any questions so far?
No questions.
Question. All right, good. So that's good. Okay, so that's the idea. Okay, so that's the idea with regards to Q learning. So now let's just take a quick look at the code. So let's bring that up then. So I'm going to open up the code. Let me actually save this this first. So I'm going to save this. All right, so let me open up the code now. I'm just going to open it in Notepad++. All right, so I've opened it, and I'm going to share that Notepad. All right, so you can, hopefully you're seeing now the code. as I said, the code it's convenient with AI Gym because you don't have to worry about the encoding of the states. You don't have to worry about the actions. You don't have to worry about the reward functions. You really can only focus on the Q-learning algorithm and how it works. However, if you were doing this on your own, like let's say you want to build a little robot car, you know, you're going to have to obviously figure out the state encoding, the reward functions, and that will be part of the challenge. So that's what, you know, that's what makes it somewhat challenging. All right, so here we have now the code. You can see, so I already described, it's not very long. As you can see here, there's only, I think, 149 lines of code, basically. Get rid of that. 161 maybe. All right, so it's pretty straightforward. Let me look at that error. I know that there's an error in here somewhere. At least I thought there was. Yeah, here it is. You see that clear here? Should be CLC. I knew I saw that. And then I modified it somewhere else, I think. Yeah, I modified it here, but it's also down here. Okay, so that. All right, so let's go over now. Let's take a look at it. So basically, you know, you can see here some of the sections. We have the library, basically, and we import. So we're going to import the gym environment, and then we create an environment, a variable called n, which is gym.make, and we call taxicab version 3, and then dot environment. So that's basically all it is. You know, once you do that, that's the version 3 of the game, taxi. It's the most current one, and so once you have n, you have everything about the environment. So for instance, you have functions like render, which renders that little grid that you saw, reset it, so restart the game, render again. If you want to print out information about the game, for instance, you want to print out the action space, you can just do n.action space, and it's going to give you the actions. Right? If you want to do the observation space, which is basically the states, you do environment.observation space, and it's going to give you information about the state. So taxicab has a lot more states than just the 16 states that are available in, and we'll talk about this on Wednesday. We'll talk about actually the state space and some of that. I'll just focus on that. But today I'm just doing kind of a high level of just focusing on the Q-learning part. So you can see, you can print out basically what are the actions, what are the states. Now, if you want to encode a state, you can. You know, you can say environment encode, and then these parameters have to do with information about the game. All right, so there's a lot of, taxicab has over 600 states, I think, and it's because there's a lot of possible combinations. Okay, there's a lot of possible combinations that it uses, and so this is something that it's a bit complex, actually. I would argue this encoding is one of the more complex parts of this, so we'll dedicate some time just to this. All right, so for now, just keep in mind there's about 500, if I remember correctly, possible states that you can be in, because it's not just about being on a specific square. It's about being on the square, but okay, are you on that square with a passenger or without a passenger? And are you on that square, and is that square where you want to pick up somebody, or is that a square where you want to drop off somebody? You know, those kinds of things. So you have to now work all of those things into the state system. And that can be a bit challenging. Okay, that can be a bit challenging. But here, you know, this just shows you. We'll look at the code of how this can be done. But this just shows you, you know, you can say, you know, I'm in this square and the taxi cab is empty and I want to pick up somebody and so on. And so then that creates the one of the 500 possible states that you have. Then once you have a state, you can assign it to the environment, and that just means that the taxi cab is now at that position, okay? And then you can render it just so that you can see it again. You know, you can also say, you know, position specific one, 328, right, out of the 500, and then that's the state. So you can print out all of these pieces of information. I basically recommend that you play with this when you start doing when you run this code, just kind of for your own knowledge. Just take a look at these parameters. Okay, so that's really just showing like the states and actions and everything. Then if we look, just right now, we're just doing an overview of the algorithm. We'll get into the details later on. The next segment is this one where you define epochs, right? So that's the number of times that you're going to run a game. You're going to keep track of penalties and rewards, right? So you're going to keep track of that. Frames, this is so that you can actually record all the information, like it's basically like screenshots of where the taxi cab is so that you can later render it, okay? So that's the idea with this idea of frames. It doesn't really have anything to do with the Q-learning algorithm. It's just for viewing. Done is a variable that you have in the game that basically means, are you done? Did you end the game? So for instance, if you were, imagine if you're the taxi cab and you picked up the passenger, did you actually not just pick up the passenger, but then did you take the passenger to their destination? If you did that, the game is over, it's done, okay? Here we have a simple example of this, right? So we can take a look at this one. So you can see here, this one is just kind of the first code is just, you know, a while loop while not done. All right, so it hasn't, nothing has happened. So that you repeat this in a loop, and what do? You go in and you take environment action space sample. So what does that mean? It means you're going to take out of the, let's say the 4 or 6 possible actions that you can take, left, right, you know, left, right, up, down, pick up, drop off, right? You pick one randomly, and then that becomes action here, right? So that becomes action, and then action runs in the environment step. So you're going to take a step with the action you just found, okay? And then that action then basically means you play the game. So it's kind of like, you know, I'm playing a video game, you know, a first-person shooter, right? So I take a shot, and then now what happens in the game? Maybe I was discovered because I took the shot, so then they're going to attack me. Whatever it is, you take the action, right? And now you kind of live with it because that action takes you from your current state to your new state. So that happens here, where the game gives you back the new state, the reward that you received, and basically whether the game is over or not. Okay? It also gives you some more information, but you usually don't use this. And then now you say, well, if reward is equal to -10, that means I got a really bad reward, and so I'm going to increment my penalties counter, right, for whatever reason. You're also going to save information about the frames, right? So you're going to save in these frames. This is a list basically. So you append to this kind of this dictionary, right? Where you have, okay, the frame is, I'm going to grab the environment and I'm going to render it, but I'm going to save it in kind of an ASCII type of information here so that I can render it later. I also keep track of what the state was, the action, and the reward. This, again, this is just so that you can render things later on, okay? And then, of course, you increment the epoch because you want to keep track of the epochs. But basically, this loop is not learning. All right, there's no Q table here. All this is showing you is how do you play the game. You take a random action every time, you run it through the game, and then you get the parameters. And that's it. That's kind of, in a simplified way, that's how you would run this. Okay. Then at the end, you can print out the number of steps taken, right, by printing out the number of epochs. So how many epochs did it take you to get to the state of done, right? And then, so you print that out. You also can print out the penalties incurred. So how many errors did you make? So obviously, if you're just randomly trying to complete the game, well, we can randomly do anything, right? You could randomly fly a plane and possibly survive. If you've never flown a plane, it's possible. I mean, you're most likely to not succeed, but it's possible, right? So so it depends on the complexity of the game. So if you're just doing this randomly, you can expect the epochs and the penalties to be pretty high. If you incorporate the element of learning in here, then, okay, that's a much better, you can expect a much better result. Does this make sense so far, guys?
So far, so good.
All right, good. So this is just an oversimplification of it. Obviously, we're going deeper and deeper into it. This is just a quick overview. So that's kind of that, right? So that one's just to show the very basic structure or mechanism of how it works. Here in this example, now that you played that, you did this and you stored maybe the frames, the next piece of code just kind of shows you how to run it. So now you can see we're going to use, I guess if you use IPython, but this I'm pretty sure I'm not using. There's a delay in here, and then the OS that you saw I'm using to clear the screen. So basically, there's a little function here. So whenever you want to print the frames, right? So you collected all these frames as you were just randomly running the taxi cab. So now down here, if you want to view the animation, you just print frames, right? And then it's going to call this function here, and this function just pretty simply for I frame and enumerate frames, OS system CLS, it clears the screen and then it renders. Every time it's going to render the frame and the data, and you can take a look at it. So that's just convenient so that we could see that little animation that we saw initially. Okay. Now that's been said, now we get to the real thing, right? So if you remember, the initial logic here, this one, did not learn. It was not taking it was taking actions randomly. I'm going to go left because I feel like it. No logic whatsoever. And then you just take the action and you run it through the environment through a step. Now in this example here, now you add the Q table. By adding the Q table, what that means is that now you will in fact take an action. Okay, take an action. So you can see that here. This is the code for the actual this. This is important because it includes the reward function. Sorry, not the reward. It does include the reward, which is here, but it includes the Bellman equation. Okay, the Bellman equation that we're, that's the mechanism that it allows to learn. So this now will have a table. Notice it's just I'm using NumPy here again. So import NumPy as an NP and NP zeros. So you initialize a table. Notice that the table is of size the observation state. Observation space, which is basically the number of states, about 500, and the number of actions, which is about 4. Right. So we'll talk about these two things next week, on Wednesday, when we finish up the algorithm. So basically here, as you can see, we are about to get into the Q learning algorithm, training and everything. Once you've done that and you've learned, then the next piece of code you see here is evaluate the agent. Now that we have learned the Q table after 100,000 tries, you can see this algorithm runs for about 100,000 iterations. And then once it's learned then you don't train again. You just basically use the Q table and you kind of measure performance. You see that? So that's basically all this is. The rest of this I'll explain on Wednesday, and I'll assign a new homework, which basically just, you will run this code and, train it, because it'll take a while to run 100,000 iterations. And then after that, you need to report the results that you see of whether or not it works or not. So we'll do this. We'll pick up here on Wednesday. Okay. So go ahead. The code is already on GitHub. So start reading through it. Make sure you understand it. All right. I will post the notes from today on Brightspace, and that's it. So we'll stop here for today, and I'll see you guys on Wednesday. Have a good day.
You have a good one. See you Wednesday.